Hey coders, welcome back. So let's try to solve one more assessment on this LeetCode platform. So this is like my, I guess, 19th video. And what we do is we come to this page, leetcode.com/assessment, and we have like these three free, I would say, online assessment, phone interview, and on-site interview questions. So they provide like sets of questions that are frequently asked. And they have like time limit also. You have to solve it like in 1 hour. You can basically to simulate a real interview experience, right? So yeah, so let's try to solve one more session on this. So let's try it again on this phone interview one. So there might be like up to three questions. So generally two questions or three questions, and we have like 90 minutes, and you try to solve, right? So the idea behind this video will be I will try to explain uh, what are the things that I already knew about that problem and that helped me to solve it, right? So for each question, I try to, I mean, give you like a hint or maybe something like, okay, you should know this thing to solve this problem, right? And yeah, let's see how it goes. Hopefully, it will go good. So okay, we only received two questions. So this happens, right? It there might be like one, two questions or three questions. Let's see. So this is the question one, and it says like we have uh, school cafeteria offers a circular and square sandwiches at lunch break, preferred by 0 and 1. Okay, so we have like in cafeteria two kinds of sandwiches. Zero is the circular one is the squared one. All students stand in a queue, and each student either prefers square or circular sandwiches. The number of sandwiches in the cafeteria is equals to number of students. The sandwiches are placed in a stack at each step. If the student at the front of the queue prefers the sandwich on the top of the stack, they will take it and leave the queue. Otherwise, they will leave it and go back to the ends of queue. This continue until none of the queue student want to take the top sandwiches and thus unable to eat. Okay. You are given two integer array student and sandwiches, where sandwich I is the type of the sandwich and student J is the preference of the JS student in the initial queue. Return the number of students that are unable to eat. Okay, so long comprehension, but it is not tough. I mean, you have to just do the brute force. So let me explain the question, what it says now. So here you see we have students, right? And they are in the queue against a cafeteria. Now in the cafeteria they have sandwiches and they stacked one after other, right? So like 1 0 0 1. So this is the sandwich. So there is a circular sandwich, there is a rectangular sandwich, and they are placed on top of each other. Now the idea is they since the students are in the queue, so the student first come and see whether the top of that sandwich pile it has its favorite sandwich or not. For example, like 1 1, okay. The top of the sandwich is like 1 and the student is also like 1, right? So he or she can eat that sandwich, right? And if he is not able to, so let's say if this sandwich is 0 and the queue, the very first student is 1 and this is 0, this student will not be able to eat the first sandwich. So what we'll do, we need to remove this student from the front of the queue to the last, and we have to keep doing this. Okay. I mean, I'm seeing this constraint, right? So there at max is like 100 students. So we can do the brute force. And if you see, even the question says like queue, right? And so we have to implement this using queue maybe. So if you see this example, let's try to understand. So students are in the queue like this, sandwiches are like this. Front student leave the top sandwich and return to the end of the line. Why? Because if you see, this student wants to eat type 1 sandwich, but sandwich currently the top sandwich is 0. So of course he will not be able to eat, right? So it will move. here. And then for this sandwich 1, he will be able to, again, he will not able to eat, right? Because this is 0. So it will also go back. Now for this sandwich 0, this will be able to eat. So that's good, right? So maybe we can remove this item from the queue and from the sandwich also. And then we need to keep doing it. So one thing is, let's say here in this question, if you see it says like three students will not be able to eat any sandwich at all. And why so? If you see there are number of ones are like four, right? And students who like sandwich type one is four, and sandwiches of type one is only three. So of course one student will not be able to eat, right? And for here two, and then here three, one max one student may not be able to eat, but it's not that simple. Maybe there will be some cases. Um, how can I explain this? Oh, this is very weird actually. Hmm, 1 1 0 0. Okay. Okay, so sandwiches are fixed kind of. Hmm. So there might be like infinite loop, right? So if the top of the sandwich is something different and all the students want different, they will keep going right, left, right, they are keep going to the back and back and back in the hope that they might get the sandwich. So yeah, I think that's the problem. So what I'm thinking is I will keep a pointer here, like in the sandwiches. Let me copy this thing. Let's try to simulate it to understand it better. Okay, I will add it like this. Now the idea is okay. So I will put one of pointer here. So this is the sandwich currently we are trying to eat. The sandwich with type one, right? And I will start from this student here, right? So from one, and I check whether they can eat. Yes, they can eat, right? So my eye will come to here, and now this student will be removed. Now, can this student eat this one? No. Can this student eat it? No. So we have to move all these elements in the last, right? So they will be something like this. And now this 0 and 0 match, that's fine. So we can remove this. And I will increment my I to here. Now this 0 0 can eat, that's fine too. I can remove this one and now I will move to here. Now here's the problem, right? Now if you see, even though we move all these students, so 1 1 0, they're not able to eat, right? So this one go here, then again one not able to eat, one go here, then again one not able to eat, one go here. And there is no way there will be any possibility to eat these remaining sandwiches. So that will be the our answer. So only tricky part here is we need to keep track that um it is not going to repeat it for many times. So I mean how we can prevent this infinite loop stuff here, right? Because if you see now number of ones is only there are only ones and we have only zero. So there is no way anyone can eat these sandwiches. Right. So whenever this is the case, when students are either complete ones or complete zero, there is no way he or she can eat the opposite one. So this is the only tricky part. Otherwise, the question is easy. Even I will categorize this question into the easy one. Let me try writing the solution maybe, and then it will make more sense. I can call this A maybe, and this is S, and I can say like get the length of our queue. And now we also need to make sure these things, the students, we need to also move students to the back, right? So we also gonna need a queue so that we can basically pull from the first and basically insert in the last, right? So queue new linked list, and we need deck actually doubly. ended queue because we wanted to insert from both in this that I mean in the head and in the tail also, right? So dick will give us the functionality, right? So in like add first or add last, peak first, peak last, right? So we can insert and remove elements from the both side in a constant time. And now let's insert the students in the queue, right? So that will be like A of A. So these are the students. I'm iterating from one, one, one. So I can simply say like Q dot offer last maybe A. So for example, from the right side, I'm inserting each of the students, right? So when 100 will be there. Now, now how we gonna prevent the infinite loop? So that is the question. So maybe I can just keep track of how many ones and how many zeros are there, right? So maybe that will help. So like int zero type of sandwich and the one type of sandwich. So this is Z and O. Now, whenever I'm inserting, I will also make sure that I'm gonna increment J and O. Basically count how many one sandwich and zero sandwiches are there, right? So something like if A equals to 0, I can say J plus plus, else O plus plus. And I can simply say like maybe for now let's move it infinitely and we're gonna check. So the current required is like s of I. And maybe I can create a k variable also. So this is the k is like this I, right? Maybe I can name it I also, but let's go with a k. So now k is currently pointing to this sandwich, right? So this is what we wanted to eat because we are not going to eat any sandwich from any place. We have to basically pick the sandwich from the top of the stack, right? So um s of k. So this is the sandwich we wanted to eat. Now happy case will be like if the current required equals to q q dot peak first. I mean this is the happy case, right? So we can simply say q dot poll first and k plus plus. This is the case when we are able to match, right? Otherwise, what we need to do is we can simply say q dot offer last q q dot poll first, right? Otherwise, pick the student from the front of the queue and move him in the back, right? So that's the idea. So this is like the happy case, and then I can just say like, okay, return n minus k plus 1 because this this is the k, right? So if we are able to only eat till this sandwich, I equals to 0. Okay, let me see my screen is it there now? Yeah. So for example, if I'm able to only eat this sandwich like 1001, so this is index will be 0, 1, 2, 3, right? Number of elements are like 6. 6 minus 3, 3. So I don't need to do like plus 1, just n minus k will be fine. Now, how we gonna prevent this infinite loop? That is the question. Now, if you see here, whenever we are able to consume one sandwich, either it is type 0 or it is type 1, I can basically increment my O and Z here also. For example, if CR equals to 0, I can say O minus minus, otherwise Z minus minus. So this is simply means, okay, no, if it is equals to 1, then O minus minus, otherwise Z minus minus. Okay, now what will be the infinite loop case? So if my O becomes 0 and the top of the stack is 1, or my one type of sandwich become 0 and top of the stack is 1, so there is no way we are able to eat any of the sandwiches. So that is what we need to take care here. something like this. If CR equals to 1 and I mean required, we want to eat the type 1 sandwich, but we already exi- remove we already use all of our one sandwich, right? So this is, then you can simply break. Or if current required equals to 0 and G equals to 0, there is no 0 type of sandwich we can break. I know it is little messier, but I hope you get the idea. Like here you see, we are trying to eat this sandwich 0, but there is nothing left, right, to eat it. There is no 0, no student who needs 0 sandwich. So there is no way we are gonna move from this to any other place. So that is why these two conditions are there. You, instead of making this while true, I can make all these conditions here also. Like while this is not true and this is not true, keep doing it. But this is more easier to read, I would say. So yeah, this is it for this one. Let's try see any compile time error. Oh, I'm not logging. Oh no 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 no! I don't want to miss it. Oh, can I log in now? No way. Actually, I haven't logged in, I guess. And if I do exit session, oh my god, no no no. Can I? No, I cannot do that. I think I missed all my recordings now. Uh, let's see if okay, okay. Now I'm able to log in actually. Let's see. Yeah, okay. Thank God. Otherwise, I have to make solve one more problem, right? Uh, okay. Now here you see we already eat all of the sandwiches. That way it is going out of bound. So I can also say like if k equals to n, then also break. And I missed that condition. Let's see again. Okay, for this one we getting 0. And what about this one? Let's compile this one also before submitting. I don't want it to miss this one. Copy this one, copy this one, and run it. Okay, I'm getting 3, right? So let's try submitting it. Okay, we are able to solve it. So yeah, I mean, I hope you like it. Um, so what is the prerequisite for this one? I would say like if you read the question 2 3 times, you will be figure out like okay, we have to pick one student from the front and put it him in the back, right? So that will give you hint like you should know your queue data structure, right? The basics, and also try to implement one in the college days that we do like a queue using array or queue using stack. That is also a good thing to understand about the queue. But yeah, for this one, I mean, just a little implementation kind of based problem. So I would say like prerequisite will be, I think Q is enough, and maybe read the question twice, and it will make sense. And there's nothing else I would say for this one. So yeah, I hope you like it. Let's move to the second question. Let's see. Okay, so this is a tree-based question. Sorry. So we have a root of a binary source tree, right? So all the elements in the left of is lesser than the root, all the elements in the right will be greater than root, right? Return the root node of the binary source tree after the insertion, and it is guaranteed that the new value does not exist in the original binary source tree. So this condition is not very relevant. It's just to make our life a bit easier, nothing else. So there may be exist a multiple valid ways as long as the tree remains a binary search tree. After insertion, you can return any of them. Now this is very good question. I still remember in my college days when I solved this one, and You okay? So let me explain the question first. So we have this already a binary search tree, and we have to insert a node, but we need to make sure that node that we are inserting must follow and must like adhere, like it will not break the binary search tree property, right? So that's why, and you cannot insert any value, right, anywhere. We have to first find its right place, and then and if you remember, it's not like if you haven't solved this problem, it's very hard to come up with because there is multiple condition, right? If you are the CS student, uh, MCA student, so you know, in either in the BCA, in the data structure course, we do this something like, okay, we have to insert one node. So first we have to find the right place, and then we also need to make sure where we are inserting. Is it a leaf? Is it there is a single node? Or there is like multiple nodes? So many conditions were there, if you remember. Um, I think that was for deletion, I guess. Here, here I don't think we have to do a lot. For example, in this tray, we have to insert 5. So I come to this root and check. 5 is lesser or 5 is greater. 5 is greater, so I will come to the here, right? 7. Now on this 7, 5 is greater is 5 is lesser, 5 is lesser. So I will come to the left, I will create the node, do the attachment, and bingo, right? Nothing. Okay, okay. For insertion, I think it's easy in the binary search tree. I was talking about deletion in a binary search tree. So like whenever you delete this node, so we have to check like, okay, is this a leaf node? Or is this have like a child? Is this have a single child? Right, if you remember. So that is more trickier and more good problem. For this one, I don't think we have to do a lot. So for example, here we have to insert 5, and where is my tree then? Hmm, okay, no problem. Yeah, but yeah, I mean, we just need to make sure we are first. Idea is first reach that position where you wanted to attach that node, and then I think rest will be the easy. So for the binary search tree problem, it's mostly DFS, right? You have to do, and I'm not sure, but let's see. Okay, when you solve binary search tree problems, when you have solved like 30, 40 problems, it you just go with the fail and you are able to solve it because in the recursion there is a concept of faith of leaf, right? So it's like you have to believe in your function, and like it will do all your work for the child what you need to do for yourself. So this is a very good idea in a recursion based problem. Maybe I will explain maybe um, how can I explain this? Okay, I can explain one recursive trick here, and it is not going to apply it for every time, but most of the time you are able to understand, right? So let me quickly explain one or two things in the recursion. So there is a concept of leap of faith in recursion. Now what's the idea? Idea is very cool. I'm saying, let's say now you have to write a recursive function um, that will print a number that will print a number from, let's say, 10 to 1. For example, if n is equals to 10, then our recursive method should print like 10, 9, 8, 7, dot, dot, dot. How you gonna write this? So you know that, okay, this will be the structure of our print method, right? So we have to write a recursive function that will print a number from 10 to 1. So if n is equals to 10, so I'm gonna print like 10, 9, 8, 7, 6, 5. Now, a very cool idea is, let's say our function already know how to solve for 9, just a very small number. So we want to print for 10, right? If n for n, if n is equals to 10, let's assume, just believe in your function that your function already know how to print the number from 98765. So I'm saying something like this: print n minus 1. And the expectation from this my method is it is going to print like 9, 8, 7, 6, 5, 4, 3, 2, 1. I have 100% belief that this will be printed by method. Now, if this is printed by that method, what I need to print? I just need to print something like this, right? N. Because this thing is already printed and I just need to print 10 just before this one. So something like this. And now this work. And now we also need to, of course, add the base case, like if n is equals to 0, return. We don't want it to print 0, but you get the idea, right? Now, let's say if I wanted to say, instead of printing from 10, 9, 8, 7, 6, 5, something like that, I wanted to print like 1, 2, 3, 4, 5. So what will be in that case? For example, if n is equals to 10, I wanted to print like 1, 2, 3, 4, 5 till 10. Again, I will assume that my this is my method, right? It knows how to print from 1 to 9. So I'm expecting from this method it will print like 1, 2, 3, 4, 5, dot 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 10, right? Sorry, dot 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 9. I know. And now I need to also print 10. So I can just below this method now I will say like system. I mean, let me write this. Okay, it's out dot print ln n, and that's it. Now here I have to make sure if n is equals to 11. I mean, you will add your base case accordingly, and this will work. So this is the idea of a leap of faith in recursion problem. So it's very intuitive. For most of the time, it works in a tree-based problem. So now here, what we need to do. I'm saying first we need to find the right place, right? So here, this is my node. Now, if root dot val, sorry, the value that we are wanting to insert is smaller than root dot val or or maybe less than equals to. So if the value that we wanted to insert is in the left side, I have to go in the left side, right? So I can just copy this method, root dot left and val, because I know this value is in the smaller side. So for example here, current my root is 4 and we wanted to insert 5. So is 5 is less than 4? No. So otherwise we have to call insert. I have already copied this one, root dot right and val. No. So something like this maybe. I can create a C node L equals to null and R equals to null. And this is my left call. This is my right call. Right. Now, when we are able to find out, maybe let's say I go here, and then I go here, and then I go here. So when it was null, I'm returning a new node, right? So something like this. If root equals to null, I will explain this one. If you haven't done this kind of problem, you will find a little difficult, but it's not actually. And L dot left. Sorry. What we need to do is root dot left. This is root dot right, and we're gonna return root. Okay. Um. So here, if you see what I'm doing, is first I'm trying to find out where we wanted to insert that value, right? So I'm doing this call. Okay, is it in the left side or it is in the right side? I'm keep moving. Like before, we have to go here, or we have to go here, we have to go here. From 7, we have to go here, or we have to go here, here, right? Now this part, whenever I call that 7 dot left, right? So 7 dot left will be null because there is nothing, and this is where we wanted to insert that node. So what I'm doing, I'm just returning there a new node. So basically, I created a new node 5, and currently there is no attachment between 7 and 5. So whatever call that reach this 5, we're gonna go to this parent root, and root dot left is equals to whatever. If we have inserted this maybe 10 maybe, so 10 call will be made from here, and this will return me the node 10, and we're gonna just attach root dot right is equals to that node. So I'm not sure. Let's see if we have any compile time error. 427135. That's fine. Let's try submitting it. Yeah. So this is, I mean, so it, uh, so I hope, okay, let me, I mean, I can iterate this one more time. So before that, let me explain this require just a DFS. If you know a DFS, it's fine. So, okay, what I am saying now, in the insertion of this binary search tree, what we have to do is we have to first find this right place. So let's focus on this left part of the tree. We have to insert 5. So 5, where will 5 come? So I know that 5 will come something here, right? 7 dot left. So I'm reaching at this position. 7 dot left is equals to null, right? So when root 7 dot left equals to null, I'm returning a new node to this call. So root dot left is equals to whatever value returned by this thing. So you can try on pen and paper and try to what we say draw one by one, and you will be able to get it. It's not very difficult. So I hope you like it. I think both are the easy problems, I would say. Oh no, no, this one is binary search tree. One was the medium. This one was easy. But yeah, I hope you like it. Let's catch up in the next one. Thank you.